I said here, I've been fairly conservative, I said recursion schemes are essentially programming patterns, but if I wanted to be really gung-ho, I could say that they were the future of programming. They were a kind of a brave new world of programming in a higher level of abstraction. And in fact, the paper that I used, I use the word recursion schemes because the paper, and I'm never going to remember this, bananas, lenses, barbed wire, and so on. That paper used the word recursion schemes, but it also talks about a calculus of recursion schemes. So these are, I'm being a bit conservative calling them programming patterns here, but they are essentially, even if we think about them as programming patterns, patterns are good because we can communicate and reason about our programs. We can reuse code and ideas. For example, learning an API already in Haskell is often very easy because it's all familiar concepts. Well, these are even more what will be familiar concepts. If they're not now, they will be in the future. I fully believe that. And we can use a catalogue of theorems to optimize or prove properties about our programs. And this point, identify and exploit opportunities, this is really the same point, but it's an important one, I think, as parallelism is a big problem in the software industry. So this is a literal Haskell talk, which means that there are certain things that I couldn't remove from the slides because I wanted the slides to compile. And I will make the source code of this available as well as the PDF. And the talk is really inspired by Jeremy Gibbons' Origami Programming, which is a beautifully written tutorial on this stuff. And I could have come up with some great slides just by basing it on his stuff. But I wanted to give some grittier, if you will, real-world examples. There's some JSON in here and things like that, which as well as some examples very not that dissimilar to the sorts of things we've done at Barclays. An overview. So there's a lot here, and I've timed this talk, and I think it's going to come out at about 1.5 hours. So what we probably could do is skip very rapidly through some of this stuff. So there is some. I probably lied when I said it was a beginner intermediate talk. I think it's definitely intermediate, and there's maybe some advanced stuff here. I hope that's okay. But it's just because there's a lot of this stuff comes up in Haskell blogs now and on the mailing list. And I suppose I wanted to really show that it's the names are scary, but it's actually the ideas aren't. So let's start. So here are the lessons. There's a lot of them. There's the controversial one on disciple instances, but that's only for convenience for generating a few instances. There's scope type variables. I like that one because I can give type signatures to where clauses and things in a convenient way. And view patterns is my favourite one, probably out of this list because I don't have to give names to things I don't want to name. And there's all kinds of things in here. Functional dependencies. I often get less code when I use this than type families in simple examples, so I've stuck with that one. But I'll explain them if I go along if people if people don't understand them. Imports, lots of imports. These are all from the Haskell platform. The applicative stuff we make a lot of use of. More imports, third-party packages. There's a few third-party packages. Databall extras is the if that Haskell should have always had. Yeah, so that bool is the if that is in Haskell is pandering to the familiar mainstream. This is the Boolean fold. This bool here. So I make use of that in this talk. There's a little bit of hash tables and parsec and pretty printing, but these aren't really key to the talk. So useful functions. I didn't know where to put these slides, so I thought I'd put them up front. But I really like the point-free style because, again, I don't like giving names to things that I don't want to name because often those names will detract from names that I think are important. A point-free style can help with that. And also it lets me get the definitions down to one line, which maybe helps me sell the fact that they're not that complicated, but I'll let you be the judge. So these are actually from Control Arrow. I don't know if you would recognise them here, but I wrote them specialised to functions, so that you probably be able to understand them more easily. These are the categorical dual of each other. So if you flip the arrows round, so D is actually B up here, and this is a co-product, either BC, and this is a product, and this arrow's been flipped, and it's all very neat and elegant. Yes, so we'll be making use of these in a few places in the talk. And then we have one that these don't really have standardized names. Function product, I don't know what that's a good name or not, but yeah, you can see what that does. And then this is sort of generalized unzip the functors. This turns out to be quite useful especially when combined with view patterns. This one, you can't really write a zip for functors and a generalized zip for them, but the unzip is very useful. Foldable, I thought I'd give a very quick refresher on the foldable and traversable because these are extremely useful type classes in practice, and they're so useful. You might ask, well, why do we need much else? So I thought I'd give a little quick refresher to these. And foldable is intuitively list-like, so you can see that it's got fold R, fold L, and they look pretty much identical to the list versions. And this is made even more useful by the fact that in GHC you can just derive the instances for this. Here's a little quick example. We've got a tree. Here's an instance which you don't need to write in GHC. You can just derive it, but I have done to illustrate how it's used. And then here's the sort of thing that we can do with some arbitrary foldable. We can replace every A in the structure with sum 1, and then we can fold it and count. So it's nice and easy to use. Traversable. This is intuitively I think about this one as fmap with effects. So if I want to map over a structure, but I want effects, then I think of traversable. It's extremely useful in practice, and we're going to create an instance for it here. You can see it's kind of a very similar structure to if you were to derive fmap, but instead you have this applicative context here. So it's pure empty, and we need the hopefully you're all familiar with the applicative syntax, but it's in building a new node with traverse applied to the left and right elements, then we need that has to happen in an applicative context. And sequence, one of the things that's mentioned in the paper is that sequence is almost, well, you can think of it as a generalization of a matrix transpose. So it's extremely useful. What if we need to access the structure? So if we're not interested in looking at things one element at a time. So that's where I'm now going to start talking about catamorphisms. So you've probably heard the term before, and I'm sure you're familiar with Foldar, and Foldar is the first example people come up with when they talk about catamorphism. It's essentially a specialized one. For a list, it's right associative. For a tree, it describes a bottom-up traversal, and it's difficult to see. It's difficult to see exactly the connection between the different types of catamorphism when they're written in a fairly ad hoc way. So one of the things that I'm going to do now is I'm going to try to write Foldar in a form that is closer to the theory. And the theory, and this is category theory, talks about a construct called an F algebra. And I won't. This is very much a practical talk, so I won't talk too much about category theory, but I will have a couple of diagrams that I think will be useful. So what I've done here is I've rewritten Foldar in terms of a term maybe, and we've got product of A, B to B. It's a little bit more verbose than it was, but it's still 2 lines. And the interesting thing is that if you look at the definition of unfold R, this term is actually, the arrow is flipped. And so we've obviously recovered some symmetry here. And I'm going to go further now, and I'm going to try to factor out the isomorphism between the list type here and using the maybe of a product with A and a product of a head and a tail. So this bit here is noise, if you like. It's boilerplate. So I've factored it out, and I've now got fold R down to 1 line. It's still a bit of a messy line because the F map is over maybe, and the product we need to map this term over the product where we don't change the A, but we do recurse into the B. So it's not the neatest line, but I think we're making some progress. And then if we were now to for example, find the length of this list, we would have to write something like this, because now we've got this thing called an F algebra. It's a single parameter passed into the Foldar this time, and we need to write this. We need to define this F algebra, so we define it via case analysis on the structure of the maybe. If it's nothing, well, this if you can see with definition of unlist, nothing corresponds to the empty list, and that's 0. And here we've got the tail, but the tail has been pre-computed for us. So the tail is already of type int. So this is because the catamorphism is right associative. So we've already done the tail, and the tail. So the length is the rest plus 1. I've gone through that incredibly quickly, but all I've done is I've written Foldar in a form that's closer to the theory, and you'll see the reason for that. So here is this is a diagram from, it's essentially a category theory, but I've used Haskell notation because sometimes, although the notation is a bit clumsier, I think there's obviously there's less learning curve. So what we've essentially done, or what I'm saying here, is that if we drew a diagram of all the types involved, and these are called objects in category theory, and we drew these arrows to represent the, in this case, functions, we could see that we want to go from list of A to sum B, and the way we did that was going around the outside. So first of all, we turned this type here, we did unlist to get the head and the rest of the list, and then we did this fmap operation here, which actually recursed into this bit here, and then we applied the algebra to get from this to that. So if we want the definition of this, we just followed the graph, i.e. we composed these arrows, we composed these functions. It was unlist that, then that, and we get to B. And this is just simply to demonstrate how expressive a fold R is. So if I wanted to implement a fold left, well then I can use, there's nothing to stop me using the carrier of the algebra as being a function. So here the carrier of the algebra is B to B, and yeah, it's I've written fold left in terms of fold R. I won't. I'll leave you to try to pick that bit in your own time. But okay, so now we're moving on to the fixed points of functors. So this is a style of programming that it's fair to say it's probably not that often. It's not traditionally been done in Haskell. I think there was some of the data type generic experimental languages used it, but it's very powerful, and I'll show you examples of that. So it gives us data type generic functions, it gives us compositional data, and the key thing is that we represent our recursive data structures, or our inductive types, using this fix wrapper here. It has to be a wrapper because in Haskell we can't have infinite types, but essentially fix f is isomorphic to this, and you'll see how you'll see how that works. So this is a little bit about what do I mean by data type generic programming? I mean that we can actually write code that works with any data type. So if you imagine things like serializers or pretty printers, these are things that often don't have any behavior that's their behavior purely depends on the shape of the data type, and it becomes by exploiting techniques from data type generic programming, we can avoid a lot of boilerplate in our code, and I think quite importantly we can capture the pattern, these recursion schemes, as a single combinator. So we're therefore in a much better position to study them and understand them. And there are limitations to this approach. It's limited to regular data types. I think the definition of that came up a few weeks ago. But essentially, if you have a nested data types, which means that on the left-hand side of your data, you've got a parameter that is different to how you're using it on the right-hand side. Then if things start to get a little bit more complicated, but it can be done, and there are new features appearing all the time. I mean, there's something called kind polymorphism that may help ease the pain of some of these more problematic areas. So here, instead of using maybe as a type to represent my lists, I'm going to use I'm going to create a type which makes things a little bit neater, and here I've created a functor instance for it as well, it's a polymorphic functor instance. I suppose you could create a bifunctor or something if you wanted to, but I don't need to do that here. And then also I've created one of natural numbers, because I'm going to use some examples that use natural numbers. So we have to create an unfixed data type. So I don't know if it's so. What fixed then does is you can see that the list f is parameterized by an r, and what I'm essentially doing when I fix this data type is replacing r with list fa. So in a sense, I'm taking the direct explicit recursion out of the data type definition and just parameterizing it with an r, and then I'm using for the previous slide I'm using fix to fix up the type, and it's exactly the same as it's a similar idea to how we use fix the function. So then the advantage of this then is that I can now write catamorphism for any data type that we can express as a fixed functor. So then the definition of a catamorphism just becomes a single line. And here's my diagram. It's much simpler and much neater. We want to go from a fixed type to A by cat-ouch, and we do that by calling unfixed fmap cat-ouch and then ouch again. And then, so the advantage then of using, if we can use this catamorphism combinator, suddenly it opens up a whole world for us. There's a if you like, there's a catalogue of laws and theorems that are available to us that we can exploit and use. And one of the most important is this catamorphism fusion law. And it says that if we have this condition, and then it applies that condition, and we can fuse H into the catamorphism, and this is the sort of thing that compilers might do, but also it's something that we can do in our own programs. Here's a little bit more of a complicated example. This time I've got a little expression language, and of course making DSLs is something that Haskell really excels at. And if I write them in this unfixed form, I hope to demonstrate in this talk that we end up with a lot of flexibility and power and data type generic functions, so that in fact it'll be the increased complexity is worth the trade-off. So here you can see that with this expression, I've parameterized out the recursion with R, so we have add R, mod R, and so on, and then I'm going to type synonym expression, which is fix expression F, which is going to replace all those R's with it'll tie the recursive knot.
Yeah.
So.
In your definition of list F, when you showed your functor instance,
Yeah.
you had CX F of XS. Yeah.
So,
Yeah.
Why wouldn't that be C F X F map F of XS?
So, sorry, here, so, yeah, sorry, here, yes?
Yeah.
Why wouldn't it be?
Why wouldn't you apply F to X and
Yeah.
then continue the F map F through
Yeah.
the F XS?
Right, because what I'm doing here is I'm creating an F map instance that I'm going to use with that catamorphism. So what I can do if I wanted to map over these lists, I'd want to change that. But I could then recover that by writing a catamorphism, which you'll see how to do after a few slides.
You can make this data type and this is a functor in two different ways.
Yeah, we can make it a bifunctor. You could also make it a bifunctor, which would allow you to then apply f here or there. But what I can do, well, I'm really going to use this type only as an unfixed list in order for the catamorphisms to work, or I should say, that in order for the recursion schemes to work. But then I could then recover map from those. That would be one way of doing it. Or I could write a bifunctor, or there are a few ways to recover that. But yes, I've just written, that functor instance is written here just for what I need to do with it.
And that's a specific version of fix.
This is an fmap instance designed to be used with the recursion schemes.
So the generic version of that specific instance there would be fix. Would be fix list f.
Fixed list f would essentially give me something isomorphic to the to Haskell lists.
But then the F map wouldn't then map over that. So the F map for that thing would be different to how you map over this.
Yeah. Okay, let's. So here are some convenience functions for. This is basically so things will compile and so on. This is what gives me the undecidable instances. But yeah, you don't have to do. You could write these. Okay, so here's an example then. This is an evaluator with a global environment. It's global because it's passed in, and the algebra now begins to look like it's almost a specification of how to map from syntax to values. It's complicated here a little bit because the carrier type of the algebra is itself a monad, is maybe int. So perhaps a simpler evaluator I should have started with would have been expression f of int goes to int. But because we have a variable and we need to do a lookup, that lookup may fail, so there's failure, and so the carrier type of the algebra is maybe int, which is why we need to use applicative style here. So. But I think this is pretty neat because it's a simple mapping from syntax to values, and there's no explicit direct recursion here at all. And as I said, we have this, we have a catalogue and shopping list of laws and theorems once we're working this way. And now here's an example expression that we might want to evaluate. I think you agree it looks quite nasty. There's fix everywhere, and this is again because Haskell doesn't allow infinite types. We needed this new type wrapper, but you could, if you wanted to construct terms in a less verbose way, you can create smart constructors, and there's a data types a la carte paper that also talks about this in great detail. And this is what the expression would look like. If it was actually rendered as a tree, and it works. Here's a pretty printer. So it's the same sort of thing, but this time the algebra is mapping the syntax to a document type. And you can see the carrier type is a document, so it, you know, the algebra is a description on how to operate on the documents. So if we've got add x, y, then we, you know, then we combine. Then x is a document and y is a document, and this whole term here is an add x, y document. And again, I think that's really, I think that's, you know, as pretty printers go, that's very clear and concise, and there's no explicit direct recursion in there. And yeah, it works fine. Here's another one, collecting free variables, and here we're beginning to reap the rewards of being data type generic, because we're only considering one case. So this expression data type could have had many constructors. In fact, the Barclays, I think we have a DSL that has 70 or so, and but we've only had to provide the one case we're interested in, and that's to collect the IDs of all the variables, and then we use Foldable to collect them all up. And another example, some of that substituting variables. Again, we only need to consider one case, and we look up the variable in the environment, in the environment, and you know, and do the substitution. And for all other cases, we just ignore them.
Actually, if it's an error. If it's a nothing.
This is, I think we're substituting expressions for expressions, yes, so then there are no values here, so this is just an AST transform. Right. Composing algebras, so it's not true in general that catamorphisms compose, but there are useful special cases. So now we have this idea of an algebra, and we want to start to write things in terms of algebras. We might, you know, ask the question, can we compose them? And here I've got an example of why we might want to do that, and that's an optimization pipeline. So here we've got an optimization to do add. Obviously we've got add 0 to e, it's e, and there's an optimization to multiplication. If we multiply 1 by e, it's e. Can we compose these algebras and do the whole thing in one traversal? Well, you know, obviously we can do them as two separate traversals, but we want to do them in one traversal, and we would need some sort of operator here to do that. It turns out that for this special case, where algebra F is in that form and algebra G is in this form, we can compose them, and the composition is dot unfixed dot. So where did I get that from? Where did I get that magic from? And I got that from the shopping list of laws. You know, and this is Catamorphism compose law. And it's usually stated in this form, but this allowed me to then do optimize fast, which is to compose them in that way. So I suppose what I'm demonstrating here is that you know, there are here is an optimization that I've done where I can sleep at night. I don't have to worry about it. Somebody else has done the hard work of proving it's correct for me. What it actually means by law, of course, is that it's imposed on the definition of a catamorphism. So you know, by definition, this is correct. So combining algebras, well, if we can't compose them, we might be able to combine them. So we might be able to do, in one traversal, we can do two orthogonal things. And there's another, again, from our shopping list of laws and theorems, there's a banana split theorem. This is another famous one, that tells us that if we want to do kata F and kata G, then we can, you know, do them in a single traversal. And I've rewritten the banana split rule using F unzip. So it's a one-liner. I stole that line from Al Cobase, so maybe that's a Roland line. I'm not sure, but and then the jewel. I try to make the jewel of that line, which is this line here. So I believe that to be the jewel of the other one, and that's a lot simpler. Yeah. And so working with fixed data types, the problem is that a lot of the types out there don't correspond to. I can't use them because they don't correspond, because they're not fixed F. But there's a nice trick we can use where we can use type classes and functional dependencies, or type classes and type families, if you want, to basically have the isomorphism between the fixed representation and some unfixed one done transparently for us. So here I've got a type class. I won't go into too much detail about how it works, but I've got the catamorphism definition here. Instead of unfixed, it's out F, where out F is an instance of this type class. And now instead of fixed F, we have T, and T is and F have this constraint here. And here's a couple of instances. The important ones is that for lists, I want to use my data type generic catamorphism on lists of A. So I'm going to create this instance. I can still use my new catamorphism on fixed F if I want by just mapping out F to unfixed. And I can also work with natural numbers by having an instance for natural numbers where the unfixed form of natural numbers is 0 and suck n. So now I'm going to talk about anamorphisms. So this is the next, if you like, the next recursion scheme. This is the categorical jewel of catamorphisms. So I guess it was something that was discovered, these are quite important because I think when you're working with streams of data, so these are potentially infinite data structures, then you're definitely in the domain of unfolds. And here I've written unfold R. So it's got the same type signature as the prelude, I believe, but I've rewritten it in terms of view patterns. And I got this trick from Ben Mosley, a colleague of mine, and he in one of our Hoodlum sessions, I think he showed that basically view patterns can help see the duality, I think.
That's gorgeous.
Yeah.
It's a fragment, yeah?
Yeah, you can see that you've got XXS on that side, and there it is on that side, and yeah, it's. Of course, you can see the duality even more clearly. In fact, when I come with the data type generic version. But before I come on to that, just a few little examples of unfold, because we all tend to use them less. But some things are quite nicely done with an unfold. So on the left-hand side we have the, if you like, the seed, and we return the value to produce plus the new seed. And here's one. I think there was a Stack Overflow question, and everyone was trying to do it with a fold R, and it was naturally just an unfold. It was much simpler. The code for it was a lot simpler with an unfold. So this is a common. We don't have this in the prelude, which is quite annoying, but it's a commonly used function. Merging lists. This is an example. I think I stole off Jeremy Gibbons, yeah, this is quite nice as an unfold. The seed this time is a pair of lists. It's a bit. There's a lot of cases to consider, but the important ones are these two here, and it's very, I think it's very easy to understand if you have a look at each individual case. But I won't dwell on that one too much. So co-recursion then, and Anamorphism is an example of co-recursion. And if the reason why that's important is because if we're using just catamorphisms, and you know they're incredibly powerful, and I hope in this talk I'll demonstrate that. You might be able to write an entire compiler just using catamorphisms. But if you were only to use catamorphisms, you have a termination guarantee. Your program will terminate as well. You know, that's one of the many guarantees you get. Likewise, if you only use unfolds, you'll have it's really a co-termination guarantee, but you'll keep producing data. You'll keep doing productive work. But of course, not everything can be done with one or the other. And so what I'm trying to do here, or what I'm trying to demonstrate here, is that I've got an anamorphism definition here, which I should have really put the catamorphism alongside it, but it's very clearly a dual. We used to have unfix here and alg there. Now we've got the co-algebra there and fix there, and the F-map stays in the middle, but this time it's ana co-alg, and co-alg, the arrow's been flipped, and it's all dual. But it's defined in terms of fix here, and that's because Haskell doesn't enforce any kind of distinction between these different types of recursion, but in type theory they are very different, and that's why in Haskell we can create an infinite list co-recursively. So we could write, you know, ones equal one cons ones. We can write things like that, but then we can attempt to sum them, and we can lock the machine up. And if we were to, what we can do is we can try to distinguish between these two types of recursions in the type layer. So this is the greatest fixed point of functor f, and here I've got ana prime, which is exactly the same, but I've just got a code fix here instead. And if you like, this means that if I'm working with streams, I might want to use this definition here to stop people trying to sum them. I mean, doing a running sum is fine, but doing a catamorphism on it is not fine. So I just wanted to sort of point that out, really, that we've got the flexibility in Haskell to mix how catamorphisms can consume anamorphisms, but it's something that if we were in Angular or Coq or something like that, we'd have to make that distinction. In a total language, you can't freely mix these ideas. And here's the anamorphism, and I've written it using codefix, but all we've done is we've flipped the arrows. So it's the same as the catamorphism diagram, but I've just reversed the arrows. So here's something that unfolds a great for. This is a co-inductive stream. I haven't given it a termination case, so it's infinite. Of course, in reality, if you're doing streams in reality, you would probably not make them infinite, but these are infinite streams, and it's an unfixed stream, so the F-map looks very similar to the F-map we had for lists, but there's no end case. And I mean, I've really defined it so that I can use codefix. That's really why I've defined the stream type. So you cannot use a catamorphism on it. And here, iterate is an unfold, and this is quite obviously an unfold. And so now we come on to Hylomorphism, and this is just a composition of catamorphism and anamorphism. I say just, but it opens Pandora's box to general recursion. So if you combine fold and unfold, you're now Turing complete. And but I think what is cool about these is that we can take any sort of recursive control structure and replace it with a data structure, and then we've got if it's a tree data structure, then we sort it for parallelism. It's a great way to parallelize code is to think of it in terms of in terms of these very high level abstract terms. So I've got an example of that. This is another law. The Cata and Ana, I can fuse them together if I want to. As I said, there's a whole catalogue of laws and things to help make our programs efficient. So I'll skip that. So this example, I got this from Sorting Morphisms, which is a nice paper that gives examples of many recursion schemes applied to sorting algorithms. And this uses the merge list unfold that we had earlier. And I think it's pretty concise. We do need an unfixed data type to model the divide and conquer that we're going to do with the merge sort, and that's this leaf tree. And the catamorphism algebra, the merge, is simply to say, well, if we have a leaf, it's a singleton list. If we have a divide step, then we merge the results. We also need an unfold, though, that will turn a list into a tree. So this unfold here uses half to turn a list into the tree. So our merge sort is therefore just high-low merge unflattened. So it's just an unfold and then a fold. And as I said, we could apply the various laws and theorems and completely eliminate this data structure if we wanted to, so it never existed. Or we might want to use this data structure as a way to exploit parallelism. There's lots of things that we can do, but I think formulating the problem in terms of these high-level combinators gives us enormous insight into what's going on and how we can actually reason about the code. So this is the one recursion scheme that I think is very useful. It's paramorphism, and the paramorphism models primitive recursion. So what I mean by that is what is meant by that is that you also get the argument that was used to compute the result. It's it's just a catamorphism, really. It's just adding more structure to a catamorphism, and here is the additional structure that's added. And here is one that where I've optimized a bit for efficiency. So but it is just a catamorphism. What many people do is they substitute a catamorphism in, and because with Haskell we can do these sorts of equational reasoning things very easily. People have substituted in a catamorphism and come up with a slightly more efficient implementation, but it is just a catamorphism. So here, I think this example explains why it's called primitive recursion, because here I'm using a paramorphism to find a factorial. 0 factorial is 1. The factorial of n plus 1 is the factorial of n times n plus 1. And this n factorial here is the previously computed values. So a standard catamorphism will do that, but the paramorphism has also given me n, the n that was used to produce this n factorial, and then that n I can then use here to do n plus 1. So I think this example demonstrates why it's why paramorphism is known as primitive recursion. Catamorphism is known as iteration by contrast. And note this definition here is just a catamorphism, it's just a fold, whereas the normal textbook definition of factorial you see is probably this, but this is an unfold and a fold. So this is, we've actually, I think this is an improvement on that because this is just a fold.
You used your on-the-fly conversion for this.
Yeah, so this is why I did the on-the-fly conversion, because I just wanted to use integers here, and I wanted to transparently, so that type of...
So yeah, n is still actually an integer, not the sub 0.
Oh yes, this 10 is an integer, yeah, as is the answer.
Yeah.
Sorry, here.
Yeah, that in there. So the paramorphism on integer still gives you the n unconverted. It doesn't convert that into the sub 0. Quite useful.
Yeah, yeah. Here's a sliding window. So this is another nice example, I think, where we're using the argument, the excess that was used to produce the sliding window for the rest of the list, but we're actually using it to implement a look ahead. It's a nice little example of how paramorphism is even useful for simple list examples.
So X is the result of the previous step.
No, that's R. Yeah. So R is the result. R is the sliding window that's already been done.
So R is the previous computation.
Yeah. X is an excess was the argument used to produce R.
Okay.
Yeah.
Just to reconstruct the X with X's.
Yeah. Yeah. And this is a really complicated example, and I should have cut it out. I just couldn't bring myself to cut it out. But it's complicated by the fact that I put in all the type signatures, because the type signatures are the documentation of what's going on. But this example, this is another paramorphism. But what it's doing is it's doing you pass in an algebra, and which is a straightforward FA to A, and it's doing a catamorphism. But it's building up a map of all the results. So you could use it to trace what happened in your catamorphism. So here I've got the evaluation algebra with a test environment. I'm calling it catatrace. It's then giving me back a map and saying, well, 2 evaluated to just 2, 3 evaluated to just 3. A, the variable was just 1, B was just 3. B plus 2 evaluated to just 5. I've now traced, I've now traced all of that, all the different steps of that evaluation, and that was just by using a paramorphism to give me access to the term, which is fix f, and then I use that as a key here. ft, as a key into the map, it uses the map as well to pull out the values to give to the algebra, but it's I think it's not much code for quite a useful function. And now I want to talk a little bit about compositional data types, and I think this really sells the idea of working with these unfixed representation of types. I mean, it's no surprise really that by taking out the explicit direct recursion that we end up with things that are more composable and more flexible. But it really, I suppose we have to ask the question: is the extra flexibility worth the pain? And I think the answer is yes. So these first two examples are obvious things we can do. If we've got many people call the unfixed forms pattern functors. They're also sometimes called signature functors, and they have lots of different names. Base functors, I've called them pattern functors here, but we can combine them in obvious ways, like the product and the co-product. So you can imagine that if F and G are two different syntax trees, one is the core syntax F and G is the sugar. You can combine it into a new syntax tree with with both F and G. And these are explored in this paper, data types a la carte. The other cases though are almost generalized versions. If I've got a pattern of slightly generalized versions of the above, if I've got a pattern functor F and I want to combine it with a co-product with any type A, well, this structure is often called the free monad, here in an unfixed form. And if I've got, and likewise, if I've got a pattern functor F and I want a product with A, then this is often called the co-free co-monad pattern. And this is in an unfixed form. So what I'll briefly do is explore why those might be useful. The first example is templating. This is templating done right, I think. If you've ever seen Java JSP or ASP, what those guys do is they basically, when you escape out of the HTML you write, gets compiled into print statements, and the code in between the HTML just becomes code in between the print statements. And there's no wonder that most of the web is invalid HTML. This is templating done right. So what we have is we have a syntax tree, but we're going to, and rather than use the name free monad, I'm going to use lots of people use the term name context, so I've called it context, term, and whole here. So we've got, imagine F is our syntax tree that represents HTML or JSON. I'm going to now create a new type where we augment it with holes. And I'll create a type synonym for the fixed version of that. We did something very similar to this in one of Peter's Hoodlum's sessions, if anybody can remember that. So here's a function to fill the holes. So now imagine we have a data structure, and we can provide it with a function A to fix F to fill those holes. That's just a catamorphism. So if we've so how can we use this to solve the problem of templating JSON? Well, we need an unfixed parser. In the appendix, I took the real-world Haskell JSON parser and I unfixed it. And then if we wanted the parser for a JSON value, would just be the unfixed parser and then fixed. If I want to compose a new templated type, well, here's the free monad, and I've got my unfixed functor F there, and the holes are going to be name, and name is just a string. So that's now my JavaScript template type. Now I need a parser for my template syntax. This of course could be a whole arbitrary language in here. I mean, if it was Java at JSP, then this p-bar could be a parser for Java. But here I've just got a very simple one that's name, that's dollar open brace name. But the cool thing is then is that I can compose the JSON parser and compose my variable, template variable syntax parser, and the result I get is now this composed data type which was basically JSON syntax with holes. And it works fine. So here I pass some JSON with $A in. This is I didn't write a pretty printer for it, so it's a bit ugly, but it's got a hole with A in it. And then I think I had to write a little lookup function, but I fill the hole with JS number 42 and run fill holes, and that's basically templating. Another example is annotating. If we're writing a compiler and we've got lots of intermediate stages of compilation where we're generating temporary information that needs to be associated, semantic information that needs to be associated with the syntax that it's relevant to. We may want to, we could just add cases into the expression data type that are temporary, but a much better way, I think, would be to annotate the tree. And here we can use the code-free co-monad structure. Here I've called it annotate. This is its unfixed form. This is its fixed form. So now just a post-it note, I think. And there's all sorts of functions we could write to strip attributes from nodes, strip all the attributes. You can see that most of these functions are either just constructors, deconstructors, or catamorphisms, and that's all that's all I'm doing here. That's why I'm flipping through so much of this code, because they're just another catamorphism. And here's a function to synthesize attributes. So synthesize goes bottom up, and it'll use this algebra here to annotate the node. And what we get back out is an annotated expression annotated with annotations of type A. And here I annotate the syntax tree with the sizes of all the nodes. So I end up with something. Oh, here's a pretty printer. I needed to pretty print the annotated nodes, and this was just another catamorphism. And then, I thought I'd render it. This was a catamorphism, so render it into LaTeX, which is in the appendix. But they're just they're all just catamorphisms, and they're just simple case analysis on each of the constructors. And here you can see this is the sizes, where here the leaf nodes are annotated with 1, these nodes are annotated with 3, and so on up to 12. This is a bottom-up annotation. Inherited attributes. These are names that are taken from the idea of attribute grammars. But the inherited attributes go top down with where you have the attribute uses a parent context. The problem we have is that catamorphisms obviously work bottom up, but that's not a problem, because if you remember when we rewrote fold left in terms of fold right, we used a higher order carrier. Well, we can do the same here. So this carrier type of the algebra takes A, which is the parent attribute, and this is each attribute takes to create the annotation. We take the parent annotation, the current node we're on, and we have the annotation for the that we're going to apply to that current node. So fix set A to A. This because I want fix F, well that's a paramorphism, so para there. Because I want it to be top down, this is carrier type of the algebra here is a function of the attribute. The actual code, though, is just this here. So P is the parent that we will eventually be given, and the new annotation, this is the function that produces the annotation, takes the parent, fits in the current node. We do have to then give that parent attribute to all the children. Of course, all this runs all this runs after the catamorphism has happened. So the traversal builds up the function that when run will work top down. So there's a lot going on here, but there's not much code, and most of the once you get used to working in this with these combinators, it's just a natural thing to do. I want a top-down traversal, right? I'm going to have a function here. So here's an example of using inherit. I'm going to annotate everything with depths. So it's const because I'm going to ignore what the node actually is. But I just want to plus 1 to the parent attribute. And what that gets you is where each node now has depth. And because both of those functions were catamorphisms, we could imagine combining them where we have inherit and synthesize done in a single catamorphism, a single traversal. So that's and I believe that's pretty much what attribute grammars tries to solve. I think that's quite cool. How all of this can be done with just a catamorphism. There are monadic variants that we could do. If you remember that evaluation algebra that I gave you, we had because we had variables, we had failure, and so the carrier was maybe int. But what we can do is we can actually define a variant of a catamorphism that does some sequencing for us. So we only have to worry about the codomain of the algebra here being monadic, and this variant uses map n instead of fmap, which is the fmap with effects. The composition of the algebra happens in the Kleisli category, which we know all about thanks to Derek's talk. But this is it's a very, very simple tweak to the standard catamorphism, which then means that I can write the evaluation algebra now with int on the left, or int here, and this only the right-hand side is monadic. But then once I've got a monadic right-hand side, well then I've got the whole transform monad transformers world available to me, and I can, here I've used reader T gratuitously, but there's all sorts of things that we can do here. It's still, I think things still look quite nice. We're still saying add xy is x plus y, multiply xy is x times y. Here we've got our nice catamorphism on booleans, bool. It's I think that's and of course there's no explicit direct recursion here. So one of the advantages of writing our code in using these standard combinators. I mean, we talked about all the laws and theorems that are available to us that we can use to optimize and prove properties, whether that's termination and so on. But there's also other cool things we can do. One of the cool things is memoization. And this is where we could have a catamorphism. If we've written everything to work in terms of catamorphisms, we could create a memoizing catamorphism, swap it out, and swap it in for our normal one, and get some, potentially trace space for time. The pure functional memoizers, and there are some really good ones, especially Connell Elliott's memo tries. But they do require that you have some way of enumerating k, because they essentially what they do is they lazily enumerate the space of k to build up a table, but to build up a lookup structure, and that's done lazily. But I think I thought that it'd be also maybe useful to demonstrate a slightly dirty way of doing it. So this memoized function here, I mean, it could use either a state monad or an st monad, but it's going to have to, either way, it's going to have a monadic term here. And I've created a memo type class that has lookup insert, and I think in the appendix to this talk I've got an implementation of that. Memo fix is what we need to modify catamorphisms, and that's just tying the recursive knot here. So yeah, this one uses the Gregory Collins hash tables, which are very fast Haskell hash tables, which are cool. And here I've got here I have a catamorphism, and I've basically fixed it, made some slight tweaks, and I can now swap this in for any other catamorphism, provided that fix f is hashable and traversable and a few other things. But you can imagine if I've written a whole bunch of code in terms of catamorphisms, then I can, if I want to add memoization, I can pretty much do it by switching this in, which I think is pretty cool. So I could quickly talk about some more of the exotic recursion schemes. This one is just a dual of the paramorphism. So when I wrote the definition, all I did is flip everything around. It compiles, that's probably correct. This one actually allows you to short circuit a traversal. So whereas the paramorphism gives you the argument, the apomorphism allows you to, when you're producing, you can suddenly deliver a final result. You can short circuit. And this was a Jeremy Gibbons example where you might want to insert, if you had an A and a list of A, and you wanted to insert A in the right place in the list of A, you don't want to traverse all of the list of A, you want to short circuit. So, I mean, the detail isn't important, but there is a short circuit term. You can see from the type here, it's either a new seed or short circuit, and that's the right case. So here is the short circuit case. But the important point really is that apomorphism is just an anamorphism. It's just an unfold. So this is just adding more structure to an incredibly powerful construct. And insertion sort is a catamorphism of that. So what's a zygomorphism? This is a I think these terms have been famously bandied around the internet as examples of why Haskell is impossible to understand. But the names are scary, but what they actually are doing isn't. And this is a kind of a generalization of a paramorphism where instead of this B here being the original term that was used to compute the result, B is the result of some other auxiliary algebra. And the zygomorphism is just this. That's it. And if you wanted to, if you define it as a recursion scheme, it's just a catamorphism with this thing, with this algebra combinator inside. So it's just a catamorphism, that's all it is. In reality, if you had, imagine your code base is full of algebras, and you want to compose them in a certain way, and we need this auxiliary algebra to work with this one, we need to combine them in this way, you might then, there is some value in having a name for that and capturing that pattern as a name. Just so happens the name's pretty scary, but it is just a name. And here is my own example of a zygomorphism. I wanted something where I could reuse the evaluation algebra as an auxiliary algebra. So imagine that we want to count the number of live conditionals that cause discontinuities due to an arbitrary supply environment. And of course we want to do this in a single traversal. This discontinuity algebra, it's just going to look at if statements, because we're trying to find discontinuities here. But the evaluation algebra is going to supply it with the a maybe int, which basically is what a term has evaluated to. So then when I do my case analysis on an if, I've got the term, what the term evaluated. So this is the true term, the test term. So the test term, what the test term evaluated to, the x term, or the true case, what that evaluated to, the y case, what the y evaluated to, and then I can have my logic here for finding discontinuities. If both true and false evaluated to something and they were the same, then this isn't a discontinuity, but I've still got to sum up the results of the true and the x and the y, because they may have also have discontinuities embedded within them. Otherwise, the common case, however, is that I take what the true value evaluated to. If it evaluated to nothing, because there are variables in the true term, then I've got a discontinuity, and then I can simply, then I've got sum 1. This is a new discontinuity, but of course I still need to sum up what happened in the test part, the true part, the false part. If however I've got if the true part, if it evaluated to a value that was less than 0, greater than 0, because I should have explained this, but we don't have Booleans. This if neg is if negative. If I have if the conditional has if the environment has meant that the conditional has that is no longer live, there's no longer variables in it, we know what the value is, then obviously we would recurse down the left branch or the right branch and ignore the other branch. And then everything else is just folding, it's just using a foldable. So I suppose what I'm trying to demonstrate here is that this method is finding discontinuities just by considering the if case, and it's reusing the evaluation algebra to do that. And the final function to find the discontinuities is zygo evaluation alg with that discontinuity case, with that if case. So it's I think it's not a lot of code for a complicated problem. And here's a little demonstration of it. Yeah, we've got a test condition with b in it, which if b is negative, then expression 1, otherwise a constant of 4. Expression 2, and this is called expression 2. This has 3 variables in it, a and b. But I'm going to supply. And here's a pretty print of E2. You can see that the first one has just b in it. But if I'm going to provide the discontinuity thing with an environment where I set b to -1, then this condition is not going to analyze this part. It's just going to look into this part, and A is a potential discontinuity, and so yeah, it's 1. Histomorphism. So we're near the end of the talk now. So histomorphism is a very exotic one. It's only been around since 1999. I think histo means history. again, it's just a catamorphism. That's all it is, but with additional structure. And we've what it does is as it does its work, it annotates the tree with all the results. So you have access to the history of the catamorphism. You have access to all the sub results and sub results. And here's an example where we compute Fibonacci numbers. So this is the so-called course of value recursion Fibonacci, because we need access to n-1 and fn-2 here. I mean, really I should have written this fn plus 2 equals fn plus fn-1, really, to be consistent with this. But I hope you can see that we've written the histomorphism exactly like the maths here, and effectively it's highly efficient memoization, because I don't even have to do any kind of hashing or anything to look these values up. I mean, they're just there. N and M are just in the data structure ready to be plucked out. So I've written the Fibonacci just like the maths, and but it's lightning fast. The constant factors may not be quite as good as another way, but it's the complexity is just right. And of course, these forms, because it's just a catamorphism, you can if we can parallelize a catamorphism or cache it or do other things to it, then all the histomorphism can reuse all of that. Another example, this was from.
So
Sure.
These algebras, are they all? So this if you had, say, a paramorphism, could you then apply this one to be the result of your left-hand term for your paramorphism, i.e. the result of the previous?
So you mean sort of a histomorphic paramorphism or something else?
I guess that's the zygote one, isn't it?
Yes.
When you apply this as the...
Yes, because let's go back to this. So if you modify this combinator here, you could by doing instead of having fmap SND here, you could make this compatible with histomorphism by just changing this algebra combinator here. And I don't know what you'd call it, histomorphic zygo or something. But yeah, it would just be. I think you would just put an attribute constructor in here, and then you'd have an algebra combinator that would work with histomorphism, and it would literally be a simple little change, and if it compiled, it would work, I'm sure. Yeah.
And it would make a great name for a band.
So that I think is cool, and I think isn't there a famous wiki page called the zygomorphic histomorph something? Yeah, but it's it's these ideas that it'll be based on. This was from the Vene paper. This is filtering out the even positions. You have to imagine the array being one indexed, but again, this is something that is surprisingly not natural to write as a simple fold. But with histomorphism, which is a fold, as we know, which is a catamorphism, but with the additional structure, it's actually fairly natural to write. Strip here is stripping away the annotations, and so we're getting access to the history, and we're skipping here. We're skipping out the first place, but then grabbing all the sub results of y, and yeah, it's the last one now. This is the last one. This is the futumorphism, which is another one from Venu, and this one is just a categorical dual to a histomorphism. It lets us build more than one level at a time. In order to use this little nice little operator here, I had to create this function. Here's the example they provide on their paper, and I've seen no other example of a futumorphism ever in the world. But we did put one in our code base, yeah. So actually there are two, yeah. So there's two in the world ever, I think. But this one, this is the example they give in their paper, and what's happening is that we're using this free monad to structure to indicate building a level that we don't want to process. So to explain the pairwise exchange, we start by building the first part of our stream, where the first component is the head of the tail. So we're saying the first component, I want to swap the one and swap. Here is 1 and 2. The first component is going to be 2. The second part, the rest of the stream, though, we're going to say term, which basically means I don't want you to. I'm going to produce another level, and that's not to be processed. And the other level is the head of x's, which I think which is 1. Which is 1 here. So we're producing another level. We've already produced 2, but we're going to produce another level 1 that we're not going to process. And then finally, to then produce something that we do want processing, i.e. a seed, the seed to continue with is whole, and whole therefore is tail XS, which is tail 3, 3. So then it's 3, but then 3 is, because we said whole, 3 is processed and eventually swapped here. Yeah, it's basically, it's an unfold, so it's, the example I've given is stream processing, but it allows us to produce more than one level at a time. With the seed that you currently have, you can produce more than one level. So you can see that, it's pretty specialist, but the only point I wanted to make, it really is that it really is just an unfold in this good extra structure. That's all it is. And the extra structure's pretty small. So we're finally at the end of the talk now. I suppose the main points are that the catamorphisms, anamorphisms and hylomorphisms, i.e. the folds, the unfolds and the refolds, they are fundamental, and they capture all of recursive computation. And these other more exotic schemes that we often hear about are just based on these terms. And I think by programming by using these, especially in a data type generic way as well, is a very powerful way of getting code reuse and therefore building reliable, efficient, and hopefully parallel programs. And I guess what we've been doing is we've been avoiding direct explicit recursion wherever possible. So we've literally built all these programs, sorting algorithms, compilers, pretty printers, templators, everything, and we haven't done any explicit recursion at all. So it's very, very powerful stuff, and I think it's the future. I believe it's the future of programming. But maybe going a bit too far for some people, but that's what I truly believe. And here's a little table of all the stuff we covered. The ana was the jewel of the kata, the apo was the jewel of the para, the futu was the jewel of the histo, and then we had the zygo. I haven't thought about what it would be, but I assume we could flip the arrows. I think it would involve
simpler than a feature.
yeah. And here are some papers that you know, to find out more, I encourage you to check out. So this has been a whistle-stop tour, and I know I've gone incredibly fast, and I should have cut the talk down. But I guess if nothing else, I wanted to demonstrate all the cool things that we could do with this theory. And these papers will always explain it much more clearly and correctly than I could. You know, and I definitely mean that. Some of them are very readable. They're all very readable and very well written, except this one, yeah. Which I put here because it's very well cited. But yeah, you probably want to come to that one last.
Please don't type that.
And sorting morphisms is quite a good one. These ones are also, I put them here because these are where the histo and the futu come from, but they're not easy reads either. And that's the end of the talk.
Tim, other than reading through the code when you post it and reading through all the papers you cited, is there kind of any tips you'd give people to trying to sort of learn this in steps? You know, are there good kind of ways to start, or is it just a case of you keep struggling until you suddenly get that light bulb moment and it all makes sense?
I think there's definitely the light bulb moment factor to it, yes. But I mean, certainly by starting with the Jeremy Gibbons stuff, which is really readable and well explained, is definitely good. But also, I think when I post the literal Haskell for this stuff, I think you know, being able to play around with some of the examples that I've given and changed them. There's no substitute to trying to write code, really. But I mean, it's a lot. It's actually very simple to use a catamorphism than it is to understand one. You know,
I think if you find yourself writing explicit recursion, say, well, how can I do this without? The same way that you sort of start doing with lists. You know, when you start using lists, you sort of read a few examples in books and you start writing recursive things, and then you realise actually fold is a more elegant way to write that. It's exactly the same here, just generalising.
You can almost learn it by playing code golf. It's kind of like I've got my explicit recursion, I've got and then I'll try and rewrite it without it.
And you'll find the catamorphisms are the easiest one to understand, and you'll start using those, and you'll try and write something that you can't actually do with a catamorphism. There's something that you really need the original C value. You need the original term at the same time. So you say, oh, hang on a minute, I need the original term. I need a paramorphism for that, and then you'll write that.
So what Jeremy Gibbons says in origami programming is that direct explicit recursion is the go-to of functional programming. The temptation to use it to get yourself to just solve the problem there and then, or to just change the code there and then is very high. But as soon as you do that, your code is therefore much harder to reason about. And then these laws, the whole shopping list of laws, no longer apply. And so this is very much about if you like, structured programming. And you can think of direct recursion as being there's a danger of it being unstructured. Having said that, you don't have to adopt all the data type generic stuff and the fix. You can leave that alone and use and write a catamorphism for every data type, and so therefore you'd have a lot more direct recursion in the code base, but you still you're still minimizing it.
That's probably a good way to start getting into this stuff, because the fix kind of clutters things, and it's just writing fold and unfold for your own data structures.
Yeah. Honestly, the example, I think it's working. And normally I use folds and unfolds always to do data types is what I find big more.
Well, the one reason why I chose to use why I chose to use them is because the definitions of the recursion schemes then become very, very simple one-liners that you can compare and contrast. And I mean, if you remember, if you think back to the catamorphism diagram, I mean, the fact that you can read off the definition from the diagram, and it is so very simple. Sometimes you need I felt that I understood catamorphisms more when I sort of studied them from the generic point of view. But
what I mean is, you start with swapping the recursion and then trying to change your data type.
oh, what in terms of my learning process?
Sorry?
Sorry.
It's how you think about it.
Well, I suppose I think Peter's right. It probably would help to think in terms of writing them by hand to begin with, I mean, we did that a little bit with the list examples, but you could try a simple binary tree and write catamorphism by hand for that data type. But I think that as I said, the advantage of the if you like the data type generic ones, the ones written in terms of functors, unfixed functors, they have the advantage of being summarized in a single line that's very, very concise, and you can take out the essence of the recursion scheme. You can factor it out independently of the data type, which does help you study it if you want to go to the next level of studying them and how they work, and how is a futumorphism different from a apomorphism, and taking out the data type specific stuff helps you there, I think.
There's one point in the middle, so you lost me a bit, but you have a couple of catamorphisms, and one of them is bottom up and one is top down.
Yes. Okay. Yeah. That's so. For example, here you mean. So this is where we use a catamorphism to construct a function. So here is the algebra for this catamorphism, and we're constructing a function. The catamorphism is running and it's traversing bottom up, but the end result is a function that was built by composing functions, and the top level function will take the parent attribute, which I'm passing in here, and then it will. And then it'll run all those composed functions, and then effectively the traversal then happens top down.
Try with this.
So the best way to
fold R and fold out.
Yeah, it was exactly what I did with writing fold R in terms of writing fold left in terms of fold R. It was the same idea. That's a famous, very famous trick.
So where do you? So I can see that the types seem the other way around from a top down. Where do you look at inherit and know that it's a bottom up versus the way before this one or after this one?
The traversal is still, the actual recursion is still a bottom up. Catamorphism, you actually call.
It's a para because I needed the.
That is still a bottom up traversal, but I think you're constructing a function, and effectively that function effectively executes top down, because the function, what the function does is to pass the parent down to the child.
So Cata is always bottom up.
Yeah. Catamorphism is always bottom up, and yes, I've been trying to go way too fast, but the important thing here is that things only happen top down when I finally run the function that I finally built. And it's a trick that you, once you learn that trick once, then you just use it over and over again. You could also use this with an unfold. Sorry.
In your day-to-day Haskell, when is the point that you decide to reach the unfixed form of the functor, or is that simply the way you work with recursive data structures now?
I'd say it's definitely not standard, and it's a bit controversial. And there are because it can make when you work with mutually recursive data types. I mean, if you I don't know if you're modeling an AST for C or something, you'd have statements as well as expressions and declarations, and you'd probably want to split those up into different data types, and some of them would be mutually recursive, and so it then becomes difficult to to then work in this way. In our code base, we have done that, but we've had to go to GADTs and higher order functors and type indexes, and I mean it works because it's all beautifully type safe, and it's all but it's arguably it has added a lot of complexity that I guess the jury would be out as to whether it was worth it. But I think that the languages can provide more support for this sort of thing. So the languages can, I mean, for example, one idea might be kind polymorphism, where you don't have to write higher order versions of functors and higher order versions of type indexed versions of foldable, traversable, map, and all these. There are things that the languages could do, and I think that some of the data type generic languages like PolyP helps make this stuff easier to do, because Haskell wasn't designed to work this way. I'm sure languages of the future will be going this way. From what I glean from the literature, I'm sure they will. But I'm trying to make myself think this way because I'm putting a bet on this being how things will work in the future. I suppose. I don't know, Ross, if you'd like to comment on that, but. But no, this stuff is. In Barclays, this stuff. We certainly used a lot of this to great effect, and the problems of mutual recursion and so on haven't been a big issue for us.
Are the benefits, just say, in kind of code reuse and stuff like that, or is it more the reasoning side of things?
I think for us it was to avoid boilerplate. So I think that's fair to say, isn't it, Peter? So when if we go back to some of the very, very early examples,
The key reason for introducing it was to allow you to put names on the recursion schemes that were going on, so you could without having to look through all the code to see what the pattern was. And it's the same argument for putting a for loop in a C or a Java program rather than using a goto. It gives you some name for that structure,
Yeah.
so you don't have to think about that traversal pattern. You can just understand what the actual transformation is.
I mean, it's what we already do in Haskell. In Haskell, we already compute factorial by doing fold r star and then 1 ... We all, and that's already swapping out control structures for data structures, and in that case, there's an unfold and a fold, and so we already do that in Haskell. In the textbooks, this just takes those ideas further and says yes, they're a good thing, and let's do everything like that. And yes, and you can see that really the win in our code base is that many problems. Here's one of collecting three variables. I mean, how could you really make it any more simple than that? I've complicated it by putting type signatures in, but I think the type signatures help explain what's going on. But it's really that there's no code there at all. There's no boilerplate there.
And to give an extreme example where we actually managed to use the futumorphism, we had a traversal to do of our data structure which has 70 constructors, where we were actually only interested in 2 of them. We were interested in one which basically sets a context that determines what we have to do for another particular node inside. So we had one sets of context, and then inside, when we hit another particular node, we have to do something with what we found in that context. And we also at the same time had to, when we were making that traversal, had to remove the nodes that created the context. So in a single pass, we were just able to do this. And futumorphism just expressed it in the actual algebra for it was like, I think 2 clauses, was it? 3 clauses?
3, yeah.
3 clauses.
Yeah.
So you find now that you spend most of your time just writing these little algebras and not all of these kind of combinations.
Yeah, all this is there. All the combination stuff, all the structures there, it's a library. And there's some, in fact, a lot of it we do this both using the ones that tend to show here, plus higher order ones. So we have a higher order library, which is exactly the same thing, but with indexed types using JLETs. So whenever we need to do a traversal, we say, well, what's the traversal we're doing here? We pick the function, we write the algorithm.
Yeah, and we exploit. We use some of the theorems that we talked about to make optimization. Do as many things as we can in a single traversal, and it's all good stuff. And we're confident in the correctness of a lot of code because we're reusing so much code. But,
you mentioned parallelism. Do you in practice do any parallelism with any of these things?
that's a good question. The answer is we don't. And I think one of the reasons for that is we have a lot of memoization that uses unsafe before my own. And, for historical reasons. But you see, the thing is that we could fix that problem because it's just our memofix function that has it, and the memofix function is used for the kata and the para and so on. So we have to change one function to fix this problem. When and if the day comes that we need to exploit parallelism, I mean, there's literally, we're far better placed, I think, than many projects would be to parallelize parts of our code base. But I think that some of the parallelism I talked about here is based on the fact that we'd be creating tree data structures. I mean, our tree data structures aren't very big; they're ASTs. So our parallelism strategies probably would be different than if you had a divide and conquer merge sort or something of a huge great data set. I think the fact that we structured our code in this way means we'd be well placed to exploit it if we had to.
Well, I think if you wanted to do it in practice, you probably have to change not the combinations, but the kata and kana or whatnot, to take extra strategy parameters.
Yeah.
There's no way that we can do it completely in a sort of ordinary way.
Yes.
Because granularity always goes in.
Yeah. No, you're right. And in fact, with the memoization, memo kata already had a ton of constraints on it. I'm not going to find it now, but yeah, the memo kata already, you had to have a quality, we have to be traversable, we have to be hashable, and already there are things creeping in there that. But yeah, the algebras would all work. Yeah, we would reuse all the algebras.
Arguments for like thresholds and all sorts of horrible things like that.
Yeah.
When to stop providing that.
Yeah, and that's something that for us would be unknown at this point.
If there are no more questions, then I think we'll just take this chance to thank Tim again.